Okay, hello everyone. So I hope everyone can see my screen and also can hear me clearly. Can some couple of people can please send me the messages to confirm
Yeah,
that you
I can see
can
and hear you.
watch the slides? Okay, good. Thank you. Okay, so good. Thank you. So last time we were talking about, actually we were trying to have a grand tour of operating system and talking about some basic stuff like, for example, how data is transferred from our devices to the CPU, right? Or how CPU becomes aware of like a particular IO device has completed the requested task, right? And we said that the mechanism for doing so is interrupt. So when our device is done completing the task, then it notifies the CPU by sending an interrupt signal, and then the CPU handles the interrupt, or it runs the ISR, which is interrupt service routine, right? And one way, and we know that there are many different kind of devices, so which means that we will have many different kind of interrupts, each with its own unique interrupt ID. So, so on the CPU side, where we have operating system running, so how generic interrupt service routine looks like, and when we say generic, it's mean the one which can take care of uh, all type of interrupts. All type of interrupts mean interrupts with any given interrupt ID. So let's have a look at this slide again. This is the slide where we left last time. So on the right side, we have, let's say we have interrupt service routine for different type of devices like memory controller, disk controller, and so on, stored in memory. So essentially, interrupt service routines are also the programs. It is a code and it is a part of the operating system. So definitely it resides in memory, right? So let's say that we have these different ISRs saved at some locations in memory. And so how things work when the operating system handles an interrupt. So on the left, you see a pseudocode, which actually says essentially the same thing which we have talked about in the last lecture, that our operating system, it keeps monitoring the interrupt signal by checking the interrupt line after executing every instruction. So here it says that, okay, execute next instruction, and then after that it checks, okay, uh, is an interrupt detected or not. So if interrupt is not detected, then you again go to the loop and execute next instruction, and then keep doing so until a point where the CPU detects that an interrupt has arrived, an interrupt signal is active. In that case, your operating system will execute this generic interrupt service routine, run ISR, where it passes the interrupt number, right? And when we look at the pseudocode of this run ISR. So in essentially it is simply a switch statement where you just make decision based on the input interrupt number or input parameter. So if it is, let's say, case one, so here we are assuming that memory controller, the interrupt arriving from memory controller is assigned an ID of one. So if that is the case, so interrupt number is one, so we invoke uh, ISR of the memory controller. If ID is 2, so then we invoke the ISR for disk controller and so on, right? So it works in this way. Last time we said that the good thing about this approach is, where of writing a generic interrupt service routine, is that one routine handles all different type of interrupts, right? But the bad thing is that this approach is slow because runtime is ON. Why? Because it depends like how many different type of interrupts are supported. So if there are different interrupts with 100 different interrupts, each with unique ID, then we will have a switch statement with 100 different cases, right? So in the worst case, let's say if the interrupt ID with 100 arrives, then your OS will check all the all the interrupt IDs one by one, and it takes time, right? So which mean that it will be slow. And again, and as we said last time, interrupts are a frequent event, which mean that as for example, when you are typing, every time you press a key, an interrupt is occurring, and then your OSR needs to OS needs to run an ISR. So if running an ISR is a slower process and it is happening frequently, so it means that overall your system will be slow, and we cannot that like this ISR is a critical function, so we need to optimize it, right? We need to handle it efficiently. So how can we handle it efficiently? For doing so, we use an alternative approach, which is known as interrupt vector or interrupt table. So the basic idea is like just like as we have seen in the previous slide, we still have ISRs of different devices, the with ISRs stored in memory, but definitely if they are stored in memory, they have a starting address. So let's say that the starting address for the ISR of the memory controller is address 1, and the starting address or the location where memory location where ISR of the disk controller is stored is address 2, and so on, address 3 and address. So it can be anything. It is not supposed to be consecutive. I'm just like trying to give you an idea. Said that let's say we know the starting address of the ISR of a given ISR, right? So then what we do is that in the memory we can maintain a vector or an array in such a way that in each array element we store the starting address of the of one particular ISR. For example, here we are starting address 1, which is starting address of ISR for memory controller, then address 2, which is starting address of ISR for disk controller, and so on, right? And these addresses, so these addresses are stored in each element, like in consecutive locations, right? So the first element of the vector or the array is at address 0 and stores the address of the first ISR. Second is at index 1 and stores the address of the second ISR, and so on, right? So how now the interrupt service handling will be, or running the ISR will be different. So the main code looks similar. So we again do the same thing, that after executing every instruction, we check whether an interrupt signal has arrived or not. If not, we continue executing the next instruction. But if an interrupt signal has arrived, so then we execute the run ISR. However, this time the body of IRS run ISR function looks different. How it looks different? What we are doing is that we are simply defining a function pointer, right? And how we are defining a function pointer, if you like, I have written this pseudocode in C. So how you define function pointer in C? Just by providing an address, right? So we know that if we have the interrupt number of the interrupt which has arrived, we have interrupt ID. So by using that interrupt ID number, we can index into the interrupt vector array. If we know the name of the array, and if we just simply put the index number into that, it will give us an address. For example, let's say the interrupt number that has been sent, or the interrupt number that has been interrupt ID that has been allocated to a particular interrupt is, let's say, 2. So if it is 2, so it's mean that we are looking at the element at index 2 of the interrupt vector. So if we look at the element 2 of the interrupt vector, so then its content will be read. So the content is basically address 3. So address 3 is actually the starting point of ISR for network adapter. So that address will be returned. So when that address is returned, so it is treated as a function pointer. So when you call this function pointer, what happens that the execution control, it moves to first instruction in ISR for network adapter, and then it will start executing. And definitely in the body of this ISR, you will have at the end the return statement, right? So when you will have the return statement, your control will go back uh, to the point from where it was called. So since it was called from here, and here you have return, so it will go back to, sorry, at this location. Okay. So now This interrupt vector based approach is more efficient. Why it is more efficient? Because now you don't need to go through a long list of if else or a long switch statement, right? So even like if you have 100 or 1,000 of different unique interrupt IDs, you can directly jump into the correct address uh, based on indexing of the interrupt vector, right? So this is faster than general routine, which we have seen in the previous slide, as subroutines are not searched or called. However, the problem with this approach is that it takes extra memory space for storing interrupt vector, which can grow with number of interrupts. Remember in the previous slide, we were not maintaining this interrupt vector table, right? So if we have like thousand of different unique interrupt IDs, then this interrupt vector will grow, the size will grow, right? And this can then become a kind of the downside of this approach. But in modern systems where we have where memory is cheap and the memory capacity is not an issue, in those cases we are more tolerable. We are more tolerating for the designs or for the options where we can which use the more memory as compared to the cases or as compared to the solutions where more time is spent, just like for example in the previous approach where we were using a general interrupt routine, right? And it takes time to go through all of the different case statements. Any questions until this point? No. Okay. Okay, now let's have a look at a different problem. Uh, Actually, a problem related to the. Let me move this zoom thing on a side so that these legends are visible to you guys. So let's have a look at a problem related to data movement between a device controller and CPU. So uh, if we look at this timing diagram, uh, sequence diagram actually. So let's say that our CPU is running and it was doing something. So it was running an application, let's say, or running a program, and then a program requested to do some IO operation from a device controller, right? And let's say to that device controller, it wants to input some data. So it tells the device controller to read a byte, and then it takes this amount of time for that device controller to read the data. Let's say let's take example of the disk controller, right? So let's say it's want to read only one byte, and it takes this amount of time for the device controller, the disk controller, to read a single byte from the disk. In the meantime, while our device controller is trying to read one byte from the disk, then if the data which is requested is not critical in the sense that CPU or the application doesn't need it for next couple of instructions, then our CPU can continue executing the next instructions, or even the CPU can switch the program. Like let's say the program A requested to read a byte, and while we are waiting for the data to become available, CPU can start executing program application B, right? So instead of staying idle, it can do some useful work, right? And once the interrupt arrives from the device controller, so then our CPU will run the interrupt service routine, right? To handle the data. And when we say to handle the data, remember we say that device controller, it copies the data from the device into its local buffer. For example, from the disk into the local buffer of the disk controller. And in the interrupt service routine, what happens is that our CPU or the operating system running on the CPU will copy the data from the local buffer of the device controller into the memory. So this is what is happening here, let's say, right? So let's say it takes this amount of time for the ISR to run. And once the ISR is completed, then our CPU can continue doing whatever it was doing before it was interrupted, right? Let's say it was running an application B, so it can start running application B, right? And then this can again happen that again an IO is requested, and again we need to read a byte, and then things keep working in the same fashion, right? You get the idea, right? So here, remember, I am putting in bracket that we are considering a slower device. Slower device mean like we are only asking it to read a byte, and it takes considerable amount of time for reading a single byte. So, right? Now let's compare it with the situation where the device controller is relatively faster. Okay. Uh, I need to move this thing. Okay. So now let's consider the same situation, but with the exception that we have a faster device controller. Okay. So faster device. So let's say that again our CPU was running an application, and then application said, okay, I want to read a single byte from the disk controller, but this time we have a faster device, and it can complete a single reading a single byte in much less time as compared to this case here, right? Then it sends back the interrupt. Now the amount of time for which the CPU was waiting for the read operation to complete is relatively small. Hence, the CPU can complete only relatively a small amount of useful work before the interrupts arrives, right? So what I want you to focus on that this part is reduced here as compared to this figure. And when I say this part is reduced, it's basically mean that the useful amount of work which CPU did before an interrupt, between it's sending a request to read a byte and receiving the interrupt, it has significantly reduced. After that, again the ISR is executed, and let's say the sequence continues in the same way. So again, since our device is fast, so it can quickly read a byte and send the interrupt. So which leaves the CPU with no option but to do a relatively a smaller amount of useful work while it is waiting for the interrupt, right? So which means that our faster device will, if I'm CPU is asking to read a byte or data like repeatedly, so it will be frequently get interrupted, and it will not be able to make any meaningful progress or make any meaningful use of the waiting time, because the waiting time itself is very small, right? So uh, how can we solve the problem? What is the problem? We don't want CPU to get interrupted frequently, right? And the situation is that our device controller is fast. So how can we solve the problem? The one option is that we can ask device controller to not read one byte, but to read 1024 kilobytes. And once it is done with reading all of them, then send an interrupt. So in this case, even if our device is faster, it will take some time, comparatively more time, to complete 1024 or 1 kilobytes, reading 1 kilobytes of data, and then sending the interrupt. So now it has opportunity. The CPU has more time to, while it is waiting for 1 kilobyte, so it can use that time to do some other useful work. For example, running another program. So let's say this was program A, which said, okay, read 1 kilobyte of data. And while this program A is waiting, CPU can start running program B. And once the data becomes available and interrupts arrive, then CPU will run the ISR and take care of the data. And again, when I say take care of the data, it will copy the data from the local buffer of the device controller into the memory, right? However, there are some issues. In order for this approach to work, we need to have a large enough buffer to read, right? So we need to make sure that the device which is whom we are asking to read 1 kilobyte of data, it has a large enough local buffer to store that data after reading it from the device, so that uh, once the whole data is read, only then it will send the interrupt. If let's say that buffer is not 1024, let's say it's only 64 bytes. So then the buffer cannot hold 1024 or 1 kilobyte of data, and it is like bound to send an interrupt after just receiving 64 bytes, right? Even if our device controller has a larger buffer, still the issue is that CPU still needs to transfer the data from the local buffer to the memory. And this increases time consumed in a ISR, right? Remember, in previous lecture, we talked about that all the device controllers, they have local buffers, and their job is to copy the data from the device into the local buffer of the device controller. And then in ISR, what happens, the data is copied from the local buffer to the memory. So even if our device controller has, let's say, this is device controller, local buffer of device controller, okay? And here you have 1 kilobyte of data, which is moved from the device into the buffer. And let's say here I'm just trying something to make thing visually, uh, to make thing visual. So here, let's say that 1 kilobyte of data is copied from the device into the local buffer of the device controller. So the next step is, so this is like first step. And then the next step will be that with the intervention of the CPU, the data is copied to memory, right? And definitely with the intervention of CPU, not independent of CPU here, which means that CPU is involved. So actually what happens is that CPU copies the data byte by byte, depending upon what is the granularity of data movement to the memory. So it reads the data, let's say byte by byte, or let's say word by word, or 64 byte by 64 byte from the local buffer of the device controller into the memory, right? And all this happens in ISR. So if you have 1 kilobyte of data here stored in the local buffer, then definitely ISR will take long time. And who is running the ISR? CPU, right? So it's mean that uh, the other programs, they will be not able to, for example, if the program B was interrupted, so program B will have to wait for a longer time until ISR is completed, right? This will slow down the execution of the program B on the CPU, right? So we don't want to do that. We don't want to have this kind of situation where program B is slowed down because of ISR handling, because ISR is copying the data from local buffer to the memory. So what is the solution, or what is the how we can resolve the problem? So for that, what we can do is that one option is that we can enable the device controller to directly data transfer from its local buffer to the memory without intervention of CPU, right? So that data can be directly moved between the device controller and the memory. And for that, we don't need any help from the CPU. So CPU is then free, and it can, for example, continue executing the program B here, right? Because the job of the ISR is basically to move the data from local buffer to the memory, and now we can do that independently of the CPU. So this is called direct memory access. So we name it as direct memory access because here the CPU is not involved. A device controller can directly send the data to the memory. CPU won't be involved in transferring data from local buffer to the memory, and once your device controller has sent all the data from its local buffer to the memory, then it will send only one interrupt per data block to the to the CPU, right? So for example, in this case, 1 kilobyte. So when in our this example, so when our device controller has transferred all of the 1 kilobyte of data to the memory, then it will send an interrupt to CPU telling that, okay, I have transferred all of the data to the memory. And as a result, what happens that our CPU efficiency increases. Why? Because earlier we were using CPU for running the ISR. And as a result of that, we had to interrupt, or we had to stop the execution of the program B. Now we don't need to do that. Why? Because we can directly transfer the data from the local buffer to the memory. And as a result, here execution of the program B can continue, right? And once the DMA is completed, then it will get only one interrupt from the DMA that, okay, uh, I have transferred the data to the memory. Any questions? No? Okay, now let's try to understand data transfer in a data transfer through DMA in a more concrete example. Uh, But before doing that, let's first have a look at how things work when there is no DMS port, when there is no direct memory access between between a device controller and the memory. So here we have an example where data transfer happens from disk to memory without DMA. Let me first explain the figure. So here you have a CPU, and it is through the memory through the bus system bus, it is connected with the disk controller and also with the main memory, right? And our job is that what we want to do is that we want to transfer data from disk into the memory, right? But we don't have DMS port, which basically mean that CPU will be involved in this process, right? So how things happen or how things work here. So initially, our CPU will send a read a data block. Definitely an application is running on the CPU which wants to read some data from the disk. So it will send a request to an IO request saying that I want to read a data block from disk, right? But that request will go to the disk controller, right? Not to the device itself, which is disk drive, right? So the request will go to the disk controller. And once the disk controller receives the request, then it will read a data block serially, that is bit by bit. So remember that disks are serial devices. So what happened here is that the data is read and then it is put in the local buffer from the disk drive into the local buffer of the disk controller bit by bit, and the data is until the required size of the data is available in the local buffer. So let's say if data block is 1K 1024 bytes, so 1024 bytes will be read from the drive and put in the buffer. Then once all of the data is read from the required data block is read from the drive into the buffer, then what will happen that your disk controller will send an interrupt to the CPU, right? But remember that at this point, we yet don't have data written in the main memory. Data is only available in the local buffer of the disk controller. So in the next step, in the fourth step, what happens that operating system, which is executing in CPU, it will then copy the data. So basically, this is ISR. ISR is a component of operating system. So it will which is executing on CPU, it will copy the data word by word in a loop from buffer to the memory, right? So like for example, one word is, let's say, 8 bytes, sorry, 2 bytes. So it will copy word by word data from this buffer into the main memory, and which basically mean that until this loop is completed. So if you have 1024 bytes and in one iteration you are copying 2 bytes, so you can divide it. So it will take 256 512, it will take you 512 iterations, right? And after since those iterations are executed by the CPU, it's mean that your CPU is busy. So it is busy in copying the data from the local buffer disk controller to the main memory. So it cannot do anything else, right? And now assume that the data you have read from the drive is not 1 kilobyte. Let's say it is 4 kilobyte. So it will take even more longer. For once the data is available in the disk controller, the fourth step will take even more longer time to complete the transfer of data from the local buffer into the main memory, right? So now have a look at how the same operation can be performed uh, with DMA. So again, we want to do the same thing, which is to transfer data from disk to memory, but with DMA support. Okay. So here, how things are different. We have everything else is same. Other than that, we have a DMA controller, right? So first, the CPU programs the DM. First, the CPU does two things. One, it sends a read data block request to the disk controller, same as in the previous figure, but at the same time, it also programs the DMA controller. So DMA controller internally, just like has different registers which need to be programmed. So for example, our CPU will send DMA controller an address, count, and control. So address is basically like from starting from what address the data needs to be read, right? Or read or written. Let's say in this case we are sending the data to the main memory, so we are saying we need to write the data to the main memory. So this address is like the starting address, starting write address in the main memory. And then count is like how many bytes starting from the first address you want to write in the main memory, right? And control is like uh, direction. For example, if you direction whether you want to send the data from local buffer to the main memory or from main memory to the local buffer. So which is like reading the data from main memory, writing the data from main memory to the drive, right? And what is the transfer unit? Are you transferring the data byte by byte or word by word or 64 byte by 64 byte? So normally in modern computers, the data is transferred between CPU and then main memory in a chunk of 64 bytes. Okay. And what IO port to use, which basically means that at what address your memory chip, main memory is connected with your CPU, right? So this information is placed first in the DMA controller. Then in second step, once you have CPU has programmed your DMA controller, then after that DMA requests the requests transfer to memory. So here what happens is that uh, it requests the local buffer that once the data is available in the local buffer from the drive, then it start the data transfer. So in the third step, your data transfers starts, but this data transfer is again in form of a loop. So what happens that your DMA is now responsible for copying let's say a word of data from the local buffer of the disk controller and copying in the main memory. Note that this is different from the previous example where your CPU was responsible for copying the data, a word of data from local buffer into the main memory. This time, no. It is the job of DMA to do this transfer. So it reads the data from the local buffer and puts it in the memory. So once it let's say it copies our only one byte, so then it will reduce the count by one. So let's say here we said initially we gave the address and we said okay, copy 16 bytes. So after copying our one byte, it will reduce the count by one, so it becomes 15. It is not zero, so it will then do the same thing, like it will copy the next byte from local buffer into the main memory and then reduce the count by one, which will become 14. So your DMA controller will keep doing so until your count becomes zero. So here, every time after your byte is copied, an acknowledgement is sent to the DMA. On receiving the acknowledgement, it reduces the count and then copies the next data, initiates the next copy operation from the local buffer to the main memory. Once your count is zero, at that time, an interrupt is sent by the DMA controller to the CPU and letting it know that the whole block of data has been copied to the main memory, right? So now this is, as I said, this is different. While your data copy operation is happening through DMA, your CPU is not busy in or not involved in the copy operation, and it can do some other useful operation. Like, for example, as in previous example where we said that program B was interrupted. So in this case, we don't need to interrupt the program B, right? While the data is being copied over. Any questions? No? Okay, so we talked about like how the data is transferred first, like how devices send interrupt to the CPU, and then how we can transfer the data between the local buffer of a device and the memory with and without the involvement of CPU. But keep in mind that uh, main memory which we use in our systems is normally volatile. Volatile mean that if you remove the power, the data stored or retained in the memory will be, the data stored in the memory will be lost. So it will not be available anymore. So, but we cannot keep our systems running all the time, right? So it's mean that we need some type of storage medium where we can put our data in a permanent way. So that those kind of storage mediums which like provide you the how to say uh, non-volatile uh, feature, they are known as secondary storage, right? And why we call them secondary storage, because and why we don't call them as main storage or main memory, because CPU cannot directly read data from the secondary storage. Uh, and CPU can only directly read the data from main memory. So through load and store instructions. So since CPU has direct access to the main memory and not to the secondary storage, that's why we have named them accordingly, like main memory and secondary storage. Because data must always be first moved from secondary storage to the main memory, and then it becomes accessible to the CPU. So main memory, it is primary storage, and CPU can access the data directly from main memory. Secondary storage, it is extension of the main memory and provides the non-volatility. So examples are like, for example, magnetic disks or even solid state disks, which are now available in all kind of like laptops. So again, the disk controller is responsible for transferring the data to and from the disk devices. Okay, so uh, but in previous slides we have talked about memory and about briefly talked about by memory and the secondary storage devices. But memory and secondary storage devices are not the only type of memories which are available in a system. We have various different kind of storage devices which are arranged in a hierarchy. And as shown in this figure, on the top of this hierarchy, you have registers, then caches, then main memory, then non-volatile memory, hard disk, optical disk, magnetic disk. The main thing which you need to focus is, or which you need to uh, uh, understand here is that as we move upward in this hierarchy, the size of our device which we are using for storing data becomes smaller and smaller. For example, registers are smallest in size. For example, if you have yeah, for example, you have seen in your uh, microcontroller course that registers are normally 8-bit, or even like in other computers or microprocessors, your registers are larger in size, for example 64-bit or 128-bit. But if you compare it with the amount of data you can store in memory, it is like nothing. Because in memories you can store gigabytes, terabytes of data, but in register you are capable of storing in one register only 64-bit, or let's say 128 bits. That's it, right? So as you move upward in the hierarchy, the size or the capacity of the device reduces. Then caches, they have relatively higher capacity as compared to registers, and so on, right? So as you move up, your storage device becomes smaller in term of capacity. How, and as you move down, they become larger in size. However, the devices towards the upper end of the hierarchy, they are faster in speed, which basically means that it takes much less time for the CPU to access data from registers as compared to caches. And accessing from main memory is more expensive in terms of time and so on. So the latency keeps increasing downward, right? Another thing that you need to pay attention to in this figure is like anything above this dotted line is volatile storage, and all the components or all the devices below this dotted line, the dashed lines, are non-volatile storage devices. So registers, cache, main memory, all of them are volatile. So if you remove the power, the data will be lost. But non-volatile memory or hard disk and everything else below below is non-volatile. Okay. So this is how the memory hierarchy of a storage hierarchy of a modern computer looks like. Definitely like each of these levels in the hierarchy are a broad topic in their own. For example, registers are cache or main memory, or how they are managed, and so on and so forth. Uh, we are not going to have a look at them because register, cache, and mostly registers and cache, they are hardware managed and they are covered more in hardware oriented courses. But main memory and non-volatile memory, they are managed, or even hard disk, uh, they are managed by the operating system, and we will have lectures on managing main memory and non-volatile memory. Managing hard disk drives, it's also a topic in operating system, but we will not be able to cover it in operating system one, uh, because we will not have sufficient time. Any questions? Okay, so caching is basically a concept, and it's the concept of copying information into faster storage. It is not only a physical hierarchy. It is also a concept which you can apply both at hardware level and at the software level. So the basic idea is that you want to copy the information into a faster storage, and so that you can execute your uh, application or program relatively in a lesser amount of time, because if data is placed in faster storage, the program can access it relatively faster, right? So, but then, as I said, there is a trade-off between size and speed. As you go up, your size reduces, but your speed increases, right? So caching is performed at many levels in a computer system, in a computer, at hardware, at a hardware, just like, for example, as we have seen here in this figure. So all of these layers are actually hardware layers. So you have register, cache, memory, non-volatile memory, all of them are hardware components, right? So it is performed, caching is performed at hardware level, and it is also performed by operating system. Uh, how, for example, operating system may in advance, operating system may have a piece of code which will prefetch the data from memory before it is actually used. Why it will prefetch? Because it can, okay, predict that this data will be required in near future. So instead of like waiting uh, f for the time when it is actually required, maybe operating system can in uh, bring the data in memory or in cache, and then use it because it is readily available at the time when it is needed. Uh, So the basic idea is that if you are caching an item in the hierarchy, so first you check that cache level, and if it is not found there, then you go down to the next level. So for example, here on the left side in in this figure, you have levels which are memory hierarchy levels, which are small and fast storage. So the storage always happens from large and slow storage level to the small and fast storage. So for example, you copy the data from main memory to the cache. Main memory is large but slow as compared to the cache. And then from cache, you can copy the data to the registers. So caches are larger but slower as compared to the registers, right? So here you have main memory, data is copied from main memory to registers, definitely through L1 and L2 are caches. So registers, they are a cache for main memory. L1 and L2 are also a cache for main memory. Then main memory acts as a cache for the hard disk, and hard disk acts as a cache for tape, right? Because hard disk caches the data which you read from tape, from the tape, then main memory caches the data which you read from the hard disk, and so on and so forth, right? So when you are looking for an item, you first look at the upper level of the hierarchy. If it is found there, then fine. If not, then you bring it from the lower level of the hierarchy. Any questions? No? Okay, if no questions, then let me stop sharing and uh, where is recording? Why can't I see recording here? Okay, okay. So this takes us to the next set of slide, which is actually for our today's lecture. Uh, Again, the objectives for this week are the same as well as we had in the last on Tuesday's class. So we just want to complete our grand tour of the major operating system components and provide a have a basic coverage of computing system. Uh, we are going to have a look at computer system architecture, uh, some basic OS operations. So like what are the responsibilities of the OS operations? And in the list of those operations, we will talk about again only like we will introduce the topic. We are not going to discuss the topic. So in those list of responsibilities, we will talk about resource management, for example, process management and memory management. Uh, and that is basically what these are the things which we are going to cover in CSCI 4120 operating system one, right? Everything else like, but that is not all which we have in an operating system. We have other responsibilities, main responsibilities of an operating system as well, like storage management, protection and security, security and protection of the data, virtualization, and so on and so forth. But we cannot cover those topics in this course. They can possibly be covered in operating systems too at some point in future. So this set of slide partially covers our learning objective one, which is about understanding the control and management of hardware resources. Okay, again, the famous picture which we have seen in previous two lectures slides, a set of slides. So the question is like, if in this kind of computer or a computer which is represented by this figure, uh, if we want to run applications on the CPU, so on this machine, then CPU is the basic resource which is needed for running an application. If you don't have CPU, definitely you cannot run an application or a process, right? But the question becomes that, okay, if that is the situation, then how can, and if I want to say like, okay, I want to squeeze more computing power from my machine, then how can I do that? And by computing my power, I mean how can I run more than one processes on on my machine, or how can I equip my machine with the capabilities so that it can run more than one processes at a time. So among other factors, it depends on how many processing units are available. But as again, when you are running when you have a computer system, it is not dependent only upon the hardware architecture or the features of the machine. It also depends upon the system software, right? Right. So that's why we are saying that there are other factors which enable us to run multiple processes at the same time on a machine. But among them, one of the factor is that we should have multiple processing units available. Because if there is only one single CPU, then it
喂，
means,
对
yeah, do you have a question?
，OK，我
Eric,
3点钟才能回来，3点钟才能从那儿出发，四
Eric,
点。
do you do you have a question, or you have unmuted yourself by mistake? Okay. So, okay, so where was I? Yeah. So if you have one CPU, definitely then you can run only one processor, one application at a time. Uh, but how can okay. Uh, so if we want to run multiple, then multiple processes, then we need to have multiple CPUs on the machine. So we can categorize the uh, architecture of a computer by in terms of like its computing power, which we measure as number of processing units, right? So we can have machines or systems which have only a single processor, or machines with multiple processors. And then those kind of machines with multiple processors, we can uh, divide them in two categories: asymmetric multiprocessors and symmetric multiprocessors. We will talk about them in a while. Then we can have multi-core systems. Remember that multiprocessor systems and multi-core systems are two different things. And within the multi-core system category, we also have a subcategory named as NUMA system or non-uniform memory access systems. We will also talk about them. Then we can have an other category which is like clusters, and we have both two type of clusters, symmetric and asymmetric. Uh, Okay, let me not talk about clusters at this point because when we let's go through the list in the same order, like from single processors, multiprocessor, multi-core, and then clusters. Okay, so what is a single processor system? By the way, today you guys also have the quiz, right? Let me check the time. Okay, we still have some time. Okay, so a single processor system is is a system where we have only single processor, and in that single processor we have a single CPU. Uh, so single processor has like a single core. Now the question is that what is a core and how is it different from a processor, like in this figure, right? So processor components, let's first talk about what are the components of a processor, and then we'll talk about then what is a core. So like typical processor components are, you have within a processor you have an execution pipeline, and then an execution pipeline has different stages, like where it uh, actually this is wrong, it should be fetch and decode. Maybe let me correct it right now because then later on I will forget. Yeah. Okay. So execution pipeline is a component of the processor, and then pipeline has different stages: fetch, decode, execute, and write back. I don't think we are going to talk about the execution pipeline and stages in this course because that is a pure hardware concept. The other components are like register file, caches, TLB, translation look aside buffer, prefetches, and so on and so forth. So there are various different kind of hardware components on the processor. However, these two components, execution pipeline and the register file, they together make a single core, right? So when we say a single processor system is the one which has a processor with a single core, so it's mean that it has a single processor. So this everything, all of these, let me use the marker. So all these components together make a processor, and then within this processor we have single core, which is shown in this rectangle, right? Uh, and now in a computer system, you may have special purpose processors. For example, you can have disk controller processor, keyboard processor. Remember, we have talked about disk controller, or we have talked about device controllers in previous set of slides. So basically, those device controllers are also processors or microcontrollers, but they are special purpose. Like they cannot do general computing, right? For example, you cannot run a Microsoft Word editor on a disk controller because it is designed only for controlling the uh, data going to and from to read data to and from the disk, right? Same is the situation for keyboard processor. So these controllers are processors, they are specific for they are like for performing a specific function. So that's why they are not considered as a regular processor in their own. And if you have these special purpose processors in a computer, it doesn't mean that that computer will be considered as a multi-processor system. It will still be considered as a single processor system because it has a single CPU, right? So also keep in mind that our operating system, it may or may not communicate with special purpose processors, right? It depends upon the features and characteristic of like disk controller or device controllers. Uh, for some of them, our operating system may be able to communicate directly with them. For others, it may not be. Okay, now what are the drawbacks? Like remember why we are talking about these different kind of computer architecture or categorization of computer architecture, because we said that we want to look at how we can increase the computing power of a machine, right? Now, what is the problem with this, and how we measure the computing power, or how can how we measure the computing power in like a very trivial ways to by counting how many number of processes I can run on my machine at the same time, right? Now, the problem with this approach is that it can run only one process at a time because I have only one CPU. So it is not a realistic architecture for modern computing needs that demand high throughput, which basically mean work done per unit time. So for example, uh, if I want to do more work in a given amount of time, then I need to have more workers who are working at the same time, right? So if I have only one worker, my throughput will be low as compared to the case where I have 10 workers. So that is also true when it comes to computers. If you have more CPUs, then you can run more applications, let's say 10 applications at the same time, and then you can get more work done, right? So what is the solution? What is the solution to the problem of like where I want to increase my computing power? I want to run more applications on my machine at the same time. So the solution is one solution is like I can use a multiprocessor system. So multiprocessor system is like where we have multiple processor chips but on a single machine. Still, I have a single computer, but I have multiple chips. So this is independent chip. This is an independent chip. So both of them are like constitute two different processors. And in each of these processors, I have one core. Remember, we have talked about it, the core in the previous slide where we said that a core is basically combination of your register file and the execution pipeline. So both of these CPU 0 and CPU 1, both of them have single core, right? And then these processors, they are CPUs, they share the main memory. So in actually we can have two different type of multiprocessor systems: asymmetric multiprocessor processing systems and the symmetric one. Asymmetric are those where yes, we still have multiple processors, but those processors are not same in their capabilities. So for example, let's say I have two processors and one of them can run both user level code and the system level code, and the other one can run only the user level code. So it's mean that they are not symmetric to each other, right? In terms of their capabilities. So if I have such a kind of machine, then I need to be careful when I'm running my system level code or operating system, and I need to make sure that the system operating system is executed, the operating system code is executed only on the on this processor, which is capable of running the system level code, right? As compared to this, we have symmetric multiprocessing, where all the processors in the machine, they are of the same capabilities and they can perform all tasks. So there is no like differentiation among them in terms of like who can do what, right? Another example is like, let's say in a machine you have two processors. One of them is for running only floating point instructions, and other is for running all other instructions. So yes, you have still two processors, but they are not of the same capability. So we will categorize them as asymmetric multiprocessors. Okay. So we said why we wanted to have this multiprocessor system, like, and here in this example we talked about only having two processor. You can have more than two, like four or so on, right? And all of them will be single core, and all of them will share a single main memory, right? Uh, so why we wanted to have multiprocessors to speed up the execution of the of our processes, right? Or execution of our application. So how much speed up we can get if we have let's say n processors at a time. So let's try to have a look at this uh, about computing the speed up. So if let's say if we have one processor and it runs p processes or p programs, let's keep it simple. Program is not exactly the process, but for time being, let's say program application is same as a process. So let's assume that we have one processor and it can run p number of processes in p cross t time, where t is the execution time for one process. So if one process takes t amount of time to compute, and then it's mean if we want to run p processes on that single processor, it will definitely take p cross t amount of time, right? Now let's change the situation and say, let's say we have n number of processors. We don't have one single processor now. We have n number of processors, and the value of n is same as number of processes or applications, right? So if that is the case, then n processors, they can run p processes simultaneously in t times, which basically I'm saying is like I can run. So let's say I have uh, these processes, not processes, processors P0, P1, and Pn. And let's say I have the n applications. So I can run application 0 on P0. I can run application A1 on P1, and I can run application Pn, application n on Pn, right? So since all of them are running at the same time, but on different processors, then all of them can complete in t time, right? So if that is the case, then the speed up will be p times t divided by t. Why? Why p times t? Because this is the time which I had, which I had for running p applications on a single processor, right? And the denominator is the time which I have for running p applications on n number of processors, right? So when I divide it, and I will get n as the speed up. So what I'm trying to say here, so we are trying to say here that if you have n processors to run uh, a given workload or a given set of application, the speed up as compared to the case where you had a single processor will be n times. So basically, more processor you have, the more speed up you will see, right? However, practically, this is not exactly true. I mean, theoretically, at a simplistic level, we can say that if you have n processors, you will have n times speed up as compared to the case of single processor. Sorry. But, oh, guys, I must stop. It's time for you to go to the quiz. I'm stopping the lecture. Immediately go to your quiz.
Canvas or
Yeah, Canvas. Yeah,
okay.
Canvas. Yeah.